Hello, my name is David Watson, and I'm going to present my paper, Rational Shapley Values, a decision-theoretic approach to explainable AI. Our basic problem setting is the following. We've got some complex model, maybe a neural network like the one visualized here on the right, used in some potentially high-stakes domains such as personal finance or healthcare. And though these models may be really accurate, they're often opaque in the sense that we can't understand the reasoning that goes into individual predictions, which is why this is sometimes called the black box problem in AI. So explainable AI, or XAI, has become an increasingly popular method in the last few years for trying to explain the predictions of such models. I'm going to look in particular at two families of solutions. One is called feature attributions, where we assign individual weights, positive or negative, to the input features to try and explain a particular prediction. And another is called counterfactuals, where we try and find individual points on the opposite side of a decision boundary that are close in some sense or similar to the target point we're trying to explain. Now, I think both these methods have really strong advantages, but they've also got some disadvantages. So feature attributions tend to treat explanations as objective deliverables, which is to say that they do not vary with anything but the target function or training data. Counterfactuals are a bit more flexible and customizable, but they can also be confusing in the sense that you can get a lot of counterfactuals for a particular point, which creates new sources of confusion and uncertainty. The method I'm going to propose, Rational Shapley Values, is a sort of pragmatic synthesis between these two. It's based very much on the Shapley value framework. That's one solution to the feature attribution problem that I'll say a little bit more about shortly. But it allows us to incorporate user beliefs and preferences in a principled way using an expected utility maximization framework. And that's sort of the decision theoretic component, which I will also explain in a bit. But first, I'm going to take a few seconds to talk about Shapley values. They were originally proposed by this guy. This is Lloyd Shapley. He's a Nobel Prize-winning economist who did some foundational work in cooperative game theory in the 50s. So the original idea for Shapley values was that it was a method for assigning credit to individual members of a coalition. In the XAI setting, we think not about coalitions of players, but about features. So it's about feature subsets and how much those features contribute to a particular prediction. So Shapley values express a given prediction. F here is maybe our deep learning model or whatever model we're trying to explain as a sum, where the phi's are the Shapley values themselves, and the jth phi corresponds to the weight assigned to feature xj at point xi. Now, you may notice that this is a sort of linear formula, and indeed, Shapley values are a local linear approximator. So even if f is some highly nonlinear function, we're going to try and find the linear tangent at that point xi, and that's what Shapley values do. In this sense, it's sort of similar to Lime and a few other methods in this area. But Shapley values are a bit different, and I'm going to give you sort of the formulas that define them. To do that, we need a value function v. This is sort of the payoff associated with a particular feature subset or coalition, which in an XAI context basically means the following. It's the expected output of our target function f, holding that subset s fixed, and letting xr vary in some way. Now, I say some way because there's going to be some distribution, that's the index dr, that determines this. And there's a bit of a degree of freedom in the Shapley value literature. I'll say more about that in a bit. But for some value of dr, we're going to let it vary and hold s fixed, and that's just what the value function gives us, is the expectation of that. So the Shapley value phi is given by this formula. I'm not going to go through the details of it, but the sort of high-level point to convey is that the Shapley value for a given feature is the weighted average of that feature's marginal contributions to all subsets that exclude it. So notable properties. We've got the efficiency property. That was the one I put a few slides back, sort of the linear sum formula. Linearity, that means with respect to different value functions. Sensitivity, also called null or dummy, just says that Shapley value will be 0 if that feature contributes nothing to any subset. And symmetry, if two different features always contribute the same amount to any subset, well, then they should be equal. Shapley values are the only solution to this problem that satisfy all of these axioms, which is why they are so popular, I believe, among practitioners. All right, I'm going to pivot for a second to talk about decision theory. And it may not be obvious why we even care about decision theory in this context. So maybe it helps to motivate it by just asking, well, why are we even using XAI tools in the first place? I think a few solutions that come up a lot, settings are sort of to audit. Maybe we're worried about bias in our models. To validate prior to deployment, make sure the model's working as it's supposed to. to discover, maybe in a scientific context, to probe our data a bit. And recourse arguably combines a few of those other goals. Now, in each of these settings, I argue that good explanations help people make better decisions. That's why we want them in the first place, is to make sure that we are making an informed decision about how to act. Now, decision theory is a certain formal framework for how to reason under uncertainty about decision making, which is why we're going to borrow some sort of fundamental concepts from decision theory here. Specifically, we've got some actions A and outcomes H. A utility function basically just scores action outcome pairs. We've also got a credence function, P, representing an agent's subjective degree of belief in some outcome H, hypothesis if you like, given some body of evidence B. Well, with those sort of components in place, the expected utility of an action is just a weighted average over all the hypotheses, where the weights are given by the credence function. The nice sort of result here is that if U satisfies the utility axioms, if P satisfies the probability axioms, well, then we say that the agent is rational, which means she will tend to maximize expected utility, which is to say she'll choose the optimal action or one of the optimal actions from among a set of alternatives. This is a really sort of fundamental result going back to the 40s, and it's just basically what rationality amounts to in a decision theoretic context. So how does this matter in XAI? Well, here's an example that might help convey the message. Say we've got two applicants with identical feature values and they're both denied credit. We use counterfactuals and find that there are two minimal perturbations sufficient for recourse. They can either increase education by 1 unit or increase savings by 1 unit. But let's say that these two individuals, though they are identical with respect to their feature values, differ with respect to their preferences. So maybe this person on the left already wants to go back to school. They've been thinking about some programs and already have those sort of lined up. This person on the right has no interest in going back to school, maybe just got a new job and intends to save a little bit more each month. Well, in this case, preferences alone are going to determine which of these two explanations is preferable or optimal for that agent. We can do the exact same sort of minimal thing with knowledge, and there are examples in the paper of this for beliefs. The basic strategy for rational Shapley values is to allow users to inform the counterfactual search and then compute Shapley values with respect to these customized inputs. So we can go beyond simple questions, objective questions, quote unquote, like why did model F predict outcome Y hat for input X, to ask more targeted, pragmatic questions, like why did the model make this prediction as opposed to that prediction for X? Why did the model make this prediction as opposed to that prediction given some conditioning set S? Or why did the model make this prediction as opposed to that given S and some restrictions on remaining variables R? To define this formally, we need to introduce the notion of a relevant subspace. I'm not going to go through the technical definition. I just want to give sort of 3 points that I want to draw your attention to. One is we need to talk about the outcome class. So if I was denied the loan, I'm interested in comparing myself to people who received the loan. The conditioning set S, maybe I'm only interested in people in my age range and income bracket to make this a fair comparison. And I need to encode some degree of variation in the remaining features R. Maybe it's completely unconstrained. Maybe it varies only as a function of S. But with those 3 components in place, we now have a relevant subspace. I'm not going to say much about reference distributions. A lot of the literature in Shapley values and increasingly in counterfactuals and recourse as well is about this. But these are all just ways that R may vary with S, basically. So there's a bit more on that in the paper if you're interested. The new axiom we're going to introduce is sort of a simple one in the decision theoretic context. We just need to define a reward function, which is to say the expected utility of a given Shapley value vector. Now, these are vectors of a subspace because they vary only with the subspace holding all other features fixed. Rationality is the axiom that just says we intend to maximize expected rewards for an inquiring agent. And the theoretical result is that when the relevant subspace is non-empty, rational Shapley values are the unique additive feature attribution method that satisfies efficiency, linearity, sensitivity, symmetry. Those are our classical axioms. And rationality, this extra one that we've added. At a high level, the algorithm for doing this is quite simple. We just got a set of candidate subspaces, utility function U, credence function P. We're going to scan those subspaces and find either that they are empty, in which case the algorithm returns fail. That's actually quite important for an objection we'll consider in a moment. Or they'll be non-empty, in which case we compute the associated Shapley value and reward, and whichever one maximizes reward, that's the explanations that we're going to go with for that case. So I do a bunch of experiments in the paper. This is from the Compass data set. I also look at some medical and credit examples. You may be familiar with these plots if you've used the Shap software before. Columns here are reference distributions, rows are classical versus rational. And the first sort of thing to point out is that there's not a huge difference globally anyway between the classical and rational Shapley values, which is what we want to see. It'd be a bit unfortunate if they came apart too much. But there are some important differences when we zoom in a bit more. So this is from a diabetes dataset example. We've got some demographic variables on the left and some clinical covariates on the right. And let's say that this one feature vector actually corresponds to two different patients. We'll call them Bert and Ernie, who are identical with respect to these measures, but not with respect to their preferences. So their utility matrices over two possible diets, going low fat or low carb, are inverted. Bert is much more happy to go low fat because he's a real carb guy. Ernie is much more happy to go low carb because he's a real meat guy. And we find that though Shapley values cannot differentiate between these two, they're just going to give the same value for both. Rational Shapley values will invert the order on BMI and MAP. MAP is a blood pressure measure. So Bert will be recommended to do his low-fat diet, Ernie to do his low-carb diet. Now, counterfactuals can in principle capture this degree of heterogeneity, but they're going to overshoot the mark, I would argue, because they'll give you actually a much larger set of possible counterfactual perturbations that can be confusing in its multiplicity. This is just a straightforward weight associated with each feature. Some objections worth considering. One, do people really have these utility and credence functions? Maybe not in the precise way that we model it in the paper, but I'd say precision is less important than coherence here. As long as we have the transitivity of preferences, we can get this off the ground. As for the credence updates themselves, there's no need for people to do that in their head or with pen and paper. Software can absolutely help in that effort. A perhaps more fundamental objection, what about confirmation bias? Is this just allowing people to get the explanation they want to hear? Not exactly, because the relevant subspace can be empty. Remember, I mentioned this earlier. That's actually a really informative result. If there's no way to meet all the constraints you have in mind, that means that your constraints are unreasonable in this context. Second of all, I'd say that the transparency of specifying our underlying assumptions about Y, S, and R is actually a feature, not a bug. Because if a bank, say, and a customer have opposite conclusions, we want a third party to be able to evaluate those assumptions and determine which are more reasonable in that particular context. Some limitations worth noting. These experiments were conducted with empirical data as opposed to generative data. Generative is really the direction that a lot of this research has gone in the last year or two, so I think that's certainly something worth exploring more. The relevant subspaces were here evaluated by grid search. That's not very efficient, especially in high dimensions. So we definitely want some kind of optimization procedure for that. And the credence updates are very simple here, but all of the machinery of Bayesian computation could be brought in for more sophisticated kind of posterior calculations. In conclusion, there are strong advantages to feature attributions and counterfactuals. I think they can be fruitfully synthesized into a single method when we incorporate agent beliefs and preferences. So rational Shapley values preserve and extend the axiomatic guarantees of classical Shapley values within an expected utility maximization framework. I'll end there. Thank you so much for your time. Happy to take any questions or comments, and please enjoy the rest of the conference. Thanks.